Okay, so today we're going to look at special right triangles. There are two special right triangles, and we're going to use these right triangles to eventually create the entire unit circle. These triangles are named by their angles. The first triangle we'll look at is the 45, 45, 90 degree right triangle. You know it has two 45-degree angles and 90-degree angle. That makes this an isosceles right triangle. In fact, it is the only isosceles right triangle. So, for the lengths of the sides, as you may recall with the triangle, if we know all three angles, the triangle is similar, meaning that we can scale the triangle up and down based upon ratios. Because we want this triangle to eventually go inside the unit circle, we want the hypotenuse, which will eventually become the radius, to be at a length of 1. That means that the lengths of the sides, and remember it is an isosceles triangle, so both legs would be the same, would be root 2 over 2. And it's the same for both legs. Root 2 over 2. The other triangle I want to take a look at is the 30, 60, 90 triangle. This triangle, again, is named after its angles, 30, 60, and 90. We have to be a little bit more careful with the side length ratios because here the angles are different. Once again, because we're on the unit circle, the hypotenuse has a length of 1. And then I like to use the following numeric number. 30 is a smaller number, so opposite the 30 is 1/2, which will be the smaller length of the side. The 60 is a larger number, so opposite the 60 is the root 3 over 2. So we have 1/2, and root 3 over 2. Both these triangles will need to be memorized with their patterns. Opposite the 30 is the 1/2. Opposite the 60 is the root 3 over 2, and the hypotenuse is 1. Now we can use these scaling factors to look at the next two examples. You see, for example, A, we have a 45, 45, 90 degree triangle. Even though this angle right here is not given, we do know it has to be 45 because all three angles need to add up to 180 degrees. We notice the side length here is 4. On the triangle that we learned, the side length was root 2 over 2. So we need to think about what was the scaling factor. How do we scale up from root 2 over 2 to 4? Well, an easy way to think of that is to draw a simple ratio. 4 times what equals it actually would be easier to do it the other way. Let me clear this real fast here. Sorry about that. Still getting used to doing the podcast thing here. So we want to get to 4. We want to start with our original that we memorize. So it's going to be root 2 over 2 times what gives us 4. Well, let's think about this here. That root 2 is awfully ugly. We don't want that anywhere near our problem. We want to cancel that. And so by multiplying out the denominator, that will allow us to cancel that root 2. It might not be proper, but it will cancel that root 2. Now, let's think how we get a 4. Well, we have a 2 in the denominator, so we have to overcome that 2. So if we put an 8 in the numerator, 8 divided by 2 is in fact 4. So the root 2's will cancel. 8 over 2 is 4. So my scaling factor, this triangle is scaled up by 8 over root 2. If you wanted to write that in a more proper way, you would say 8 root 2 over 2, or just 4 root 2. So we can use our scaling factor as 4 root 2. Now, how does this relate to x and y? Well, simple. It's an isosceles triangle. The legs are the same. So therefore, x must be equal to 4. Similarly, y, we know on our original scaled triangle, y was equal to 1. We're scaling this triangle up again by 8 over root 2, or we reduce down to 4 root 2. So we simply multiply 1 times 4 root 2, which is pretty simple. That's simply going to be y equals 4 root 2. We would call this triangle solved because we now have all 3 sides and all 3 angles. Let's look at another one, same concept. So now instead of having a 45, 45, 90 triangle, we have a 30, 60, 90. Again, we know that missing angle. It can only be one thing. It can only be 60 because that completes our special triangles. And we're only talking about special triangles here. Now, normally, opposite the 30 is the 1/2. This triangle's been scaled up. It's now 2. So what scaling factor got us from 1/2 to 2? Simple. We're scaling this triangle up by 4. So 4 is our scaling factor. Now, the original hypotenuse was 1. Since we're scaling this triangle up by 4, we multiply the hypotenuse by 4. So 1 times 4 is simply 4. Likewise, y is opposite the 60. Normally on our original triangle, the value opposite the 60 was root 3 over 2. But now we're going to scale it by 4, which means multiply it by 4. So we get 4 times root 3 over 2. So 4 times root 3 over 2. 4 divided by 2 is 2, so my final answer is 2 root 3. And this triangle is now solved. So those are our special triangles. We will be coming back to them time and time again in this class. Next up, let's look at our trigonometric identities. We have 6 trigonometric identities: sine, cosine, tangent, cosecant, secant, and finally cotangent. We will be talking about these a lot in class. So sine is defined as the opposite side over the hypotenuse. Cosine is defined as the adjacent side over the hypotenuse. Tangent is defined as the opposite side over the adjacent side. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. An easy way to remember this is with the following phrase. So, S-O-H, ka, C-A-H, toa, T-O-A. And that simply stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Now, how does this relate to a triangle? Well, that's simple. Here's our triangle. Theta, notice how it says tangent theta, cosine theta, sine theta. That tells us we are talking about theta. So our eyes is over here by theta. And conveniently left, theta even kind of looks like a little sideways eye. So here's theta. Well, hypotenuse is always very easy to point out. The hypotenuse is always opposite the 90 degrees. Always, 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 always. Your side adjacent is the side touching your angle. So we have the hypotenuse, we have the adjacent side. The opposite side is the side way over here. That would be the opposite. So adjacent, hypotenuse, opposite. So if we were talking about the sine ratio, sine is the opposite side over the hypotenuse. I would take the value of this side and divide that by the value of the hypotenuse. In fact, let's go ahead and try that right now. So here we have a triangle in example 2. I notice I have all my sides, 6, 8, 10. Notice they also threw us for a curveball. They moved theta up into this angle, but same thing. I can find my sides simply enough. 10 is clearly the hypotenuse. It's opposite the 90 degree. 6 is my adjacent side because it's touching the angle. And 8 is kind of by itself, way on the other side, so it's definitely opposite. So to find the sine of theta, I simply look at my thing. Sine, so, is opposite over hypotenuse. Opposite is 8. Hypotenuse is 10. So sine is simply 8 over 10. And you can reduce that. Cosine, similarly enough. Cosine, ca, is adjacent over hypotenuse. I look at my adjacent side. My adjacent side is 6. So I would write 6. And my hypotenuse, again, is 10. So it would be over 10. And again, you can reduce that. Tangent is TOA. TOA, opposite over adjacent. My opposite is 8. Got a little equal sign here. And my adjacent is 6. Now, believe it or not, once you reduce these numbers, I have almost all of my work done. To find the remaining trigonometric functions, I simply need to take the reciprocal. So the cosecant of theta is simply going to be the reciprocal, so 10 over 8. Likewise, the secant would be the reciprocal of cosine, so it would be 10 over 6. And finally, the cotangent would be the reciprocal of tangent, which would be 6 over 8. Notice how I have theta for all my angles, because we're talking about the angle theta. And these are what the ratios equal, so I say sine theta equals. Be very careful. A lot of people will cheat the system and they'll just write sine theta 8 over 10. And that would not be correct, because the correct terminology here would be sine theta equals 8 over 10. We have one last example we're going to look at today. This example, they tell us the cosine. The cosine of theta is 8 over 17. And they want us to find, you can cross off the word calculator here, the other trigonometric functions. Well, how do we do that without a triangle? Well, simple. If we're not given a triangle, we need to create a triangle. So we're going to draw a triangle here. So just draw a very simple, hopefully nicer than that triangle. Let me try that one more time here. See if I can draw a nice, neat triangle. Nope, not quite. Almost. Okay, that's slightly better. Let me put my angle in. Now I gotta pick where theta is gonna be. I can pick theta here or by here. Normally by convention, we put theta here. Okay, now let's think about what cosine is. Cosine is adjacent over hypotenuse. What does that tell me? Well, my adjacent side is 8, and my hypotenuse is 17. Because that's what cosine is, adjacent over hypotenuse. It's a ratio. Uh-oh, I'm missing the side opposite. Well, to find the side opposite, I can use good old Pythagorean theorem. We have a right triangle here, so then I can just solve for it. So 8 squared plus the opposite side squared equals 17 squared. You would solve for the opposite side. Once I have all three sides, then it becomes just like the previous example where I simply have to write down the other ratios and take the reciprocals to find the cosecant, secant, and cotangent. So that's going to be it for this edition. Tomorrow we'll take a look at finding reference angles and applying these relationships to the unit circle. So until then, study hard.